This is the fourth in a series of resources on integral calculus. We define the idea of an integral. We investigate the fundamental theorem of calculus and look at some basic rules for integrals. We explain the difference between definite and indefinite integrals, looking at a basic example. We consider using Riemann sums as a method for approximating a definite integral. We investigate the integrals for specific function forms, including polynomials and trigonometric functions. We will also look at substitution methods to simplify certain integrals. Suppose we want to find the integral of x squared in the region from x equals 1 through x equals 3. As we discovered in the first resource on integrals, this means we want to find the area between the graph and the x-axis in that range of x values. However, in the earlier resource, the upper boundary was always a straight line, either a constant value or some linear function. In this example, the top boundary is curved. We will need to use some sort of approximation to find this area. One way we can approximate this area is to create a rectangle whose height is the function value for one of the region's endpoints. If we choose to use the right endpoint, the rectangle is said to be circumscribed. For our example, this means that the height of the rectangle will equal to 3 squared, or 9. To find the area, we multiply this height by the appropriate width of 2, so we have an approximate area of 18. Looking at the graph, this approximation is not very good, because we have a lot of extra area that is not actually between the curve and the x-axis. What happens if we use the left endpoint? If we use the left function value to create the rectangle is said to be inscribed. With our example, we approximate the height of the rectangle by the function value for the left endpoint. We have 1 squared, which is 1. The area of the rectangle is therefore 1 multiplied by 2, or 2 square units of area. However, we seem to be missing a lot of the area under the curve. How can we get a better approximation of the area? What if we split the region into halves? Instead of finding the entire area, what if we consider the region from x equals 1 to 2, and the region from x equals 2 through 3? Using inscribed rectangles, we have heights of 1 and 4 for the two different rectangles. Both rectangles have a width of 1 unit. Completing the calculations, we have a total area of 5 square units. Looking at the graph, we appear to have less missing area than we did by approximating with only one rectangle. Can we get a better approximation yet? What if we split the region into 4 pieces? The width of each rectangle is 1/2. The heights of each rectangle are the function value at the left endpoint, or 1 squared, 1.5 squared, 2 squared, and 2.5 squared. Calculating, we find an approximate area of 6.75. Again, we seem to be missing less area from under the curve. And if we split the region into 8 pieces, the width of each rectangle is 0.25. Since we are using inscribed rectangles, the height of each rectangle is given by the function value for the left endpoint for each. Plugging in and completing the calculations, we find an approximation for the area of 7.6875 square units. The larger the number of rectangles used, the smaller the error in calculating the total area. If we used 16 rectangles, we find an approximation of 8.172. With 32 rectangles, our approximation becomes 8.418. The exactness of our approximation is limited only by the work involved in finding the function values. When completing the work by hand, we may likely want to remain in the under 10 rectangle region. If we could program a computer to do the work for us, we can use many more rectangles to approximate our area. The general process for approximating the integral is to create a Riemann sum. These sums introduce some excellent notation. The basic idea is to break the region of integration into n number of rectangles. If we do so, then the integral from x equals a to b of the function f of x with respect to x is approximately equal to the sum from I equals 1 through n of the function of x sub I star multiplied by delta x. This delta x is the difference of b minus a divided by n, or the overall width of the area divided by the number of rectangles we want to form. The x sub I star is some prescribed value in each region. In the example we considered earlier, we use the left endpoint as the value for which we find the function value. Let's see one more example using Riemann sums to find an approximation for an integral. Suppose we want to find the area under the curve for the function f of x equal to 4x minus x squared from x equals 0 through 3. We want to use a Riemann sum to approximate this area, and we'll split the region into 6 rectangles. This means that our delta x will equal the quantity 3 minus 0 divided by 6, which equals 0.5. So our Riemann sum will be the sum from I equals 1 through 6 of the quantity 4 times x sub I star minus x sub I star squared multiplied by 0.5. Plug in the appropriate x values. Calculating, we find an approximation for the integral of 8.125.